Greetings, minions. Welcome again. This time, it's all about significant figures. I've had to throw this up there just to ensure that YouTube doesn't get. I can't say any of those phrases. Sorry. Never. So the YouTube doesn't reject my video. How's that? Okay. So here we go. Significant figures. All about what matters and what doesn't when it comes to measurements. We use significant figures to help demonstrate the level of precision that we had during our experiment. We take measurements during our experiments and they have to convey some level of precision. And we do that through the use of significant figures. There are several rules for dealing with individual measurements. And here's the first. For taking an individual measurement, if the zero in your measurement is between other non-zero digits, it is significant. Example there is 50.3 has three significant figures, the 5, the 0, and the 3. Note that decimal does not matter for this rule. 3.0025 seconds has 5 significant figures. If there is a 0 between other non-zero digits, it's significant. Second rule, zeros in front of non-zero digits are not significant. So, in the example of 0.892 kilograms, there are only 3 significant figures. The 0 in front does not count. Just as 0.0008 milliseconds also only has 1 significant figure for the same rule. Leading zeros, zeros in front, zeros to the left, however you want to say it, if they are in front of non-zero digits, they are not significant. Zeros at the end of a number and also to the right of the decimal are significant. So if I'm looking at an example of a measurement like 57.00 grams, it has 4 significant figures. 5, 7, 0, and 0 are all significant. Just as 2.000000 kilograms will have 7 significant figures because all of those zeros are at the end of the number and to the right of the decimal. Zeros, this is our fourth rule. Zeros at the end of a number but to the left of the decimal are not significant unless they were measured. So we have to use some mechanism in order to explain that our zeros which are at the end and to the left were significant if they were measured. The examples I have there are 100 meters or 1,000 meters has 1 significant figure. But if I place a small dash above the 0 that represents the last measured digit, then 1,000 meters with the dash above the middle 0 indicates to me that not only is that 0 significant, but the one in between the 1 and that 0 would also be significant. So there are 3 sig figs in 1,000 with a dash above the second 0. The second way to do this is to say 20 meters has 1 sig fig, but we know that if we add the little tiny decimal right there, then I know that that 0 was measured and it is significant. So therefore 20 with a decimal has 2 sig figs. I don't care which one you use. It usually depends on the situation. Alright, so those are the rules for individual measurements. Now we have to consider the rules for when we perform calculations on our measurements. Suppose we're going to do some addition and subtraction. I'm going to explain this the best I can verbally. This is right out of the textbook. Go to the first column from the left of the final significant digit. For instance, if I take 97.3 and I want to add 5.85, I would set it up like this. I would draw a vertical line from the left of the final significant digit. I would actually word this differently. I would say the measurement with the least precision. Draw a column at the end of that number. And here it is. The number with the least precision is this 0.3. It's in the tenths column. This 5 is in the hundredths. my vertical line for determining significant versus just used for rounding is at the end of the last number with the least precision. Right there. So my answer is actually 103.2 with the correct significant figures. This rule is fairly complicated. The word and the verbiage stuff is, I think, only adds to the confusion. This visual is the best way to imagine how to draw your line. Go to the number with the least precision, tenths versus hundredths. When that's the case, draw your vertical line after the one with the least precision. Everything to the left of that line is significant, everything to the right is rounding. The other thing we might be able to do is multiply or divide, and this is a much easier rule. Now, all I need to do is identify the number of sig figs in each measurement, and my final answer has to have the same amount as the measurement with the least. So if this has 2, 2 and 6, and this has 4, remember, zeros to the left, not significant, my answer from the calculator is 0.67184. But with the correct number of sig figs, it is 0.67. I'm going to mention rounding here real quickly. There are multiple conventions. In other words, there are different ways to perform rounding. Rather than complicate, we've already just gotten through a rather complicated set of rules for managing sig figs in our measurements. I am going to allow the use of straightforward rounding. In other words, if it's a 0, 1, 2, 3, or 4, the previous digit doesn't change. For instance, if I have 0.543, it would round to 0.54 with 2 sig figs. And if I have a 5, 6, 7, 8, or 9, the previous digit will round up. So 0.545 rounds to 0.55 with 2 sig figs. The rules for sig figs are about managing your zeros. If you're curious as to whether or not your zeros count, that's when you have to consult the rules. If you make a measurement and it has actual non-zero digits in it, they're always significant. You measured it, they exist. They are real numbers. They are legitimate measurement numbers. It's the zeros you have to worry about. Okay, so that's it for sig figs and rounding. See you in class.